So I think we should get started, and well, I know most of you because you've been in a class with me before. So this class is about general relativity, and we're going to discuss the foundations of the theory. We're going to do a little bit of special relativity at the beginning, and then after developing, the general principles, which involve a lot of math, tensor calculus, writing down the field equations, we're going to look at applications of GR, which include all sorts of astrophysical and cosmological ideas, which have to do with black holes, the evolution of the universe, and other things that are of great interest today. So the outline of the course is here. I think you will find a lot of this information on the course webpage. So if you go to EEE, you will find a copy of this document. Now, this outline is somewhat ambitious because I think we are not going to be able to cover all the wonderful things that I mentioned here because of lack of time. In fact, some people, when I tell them that I try to teach general relativity in a quarter, are rather surprised because the number of places, usually it's a semester, if not 2 semesters. So we're going to cram a lot of stuff into a relatively short time, in about 20 lectures. And so the principle is that we would like, at least my desire in the framework of this class, is that we'd like to understand the basic principles. What guided Einstein in constructing the theory of general relativity, and how unique is it? I mean, are there other possibilities? And what are the main ideas? How solid is the foundation of general relativity? How solid are its predictions? And so we will be focusing more on fundamental issues rather than a long list of possible applications, which we really don't have the time to do. So nevertheless, there are some very important aspects of it, like black holes. So we'd like to understand, what exactly does GR, what exactly does Einstein theory tell us about black holes and cosmology as well, and things like that, and what is it that it doesn't tell us? What else perhaps has to be added or is missing or is poorly understood one way or another, right? So nevertheless, in order to understand the theory, we need some mathematics. I mean, it turns out that general relativity requires some understanding of tensor calculus. That is, in order to understand, the foundations of Einstein theory and why it is, in fact, unique, we need to understand this mathematics that comes with it, which is not trivial, but nevertheless is an essential part of it. In other words, you cannot discuss general relativity without tensor calculus and differential geometry. And so we're going to spend some amount of time on that, right? And we will not have sufficient time to prove everything, so I think you will see that in a number of occasions I will use the famous phrase, it can be shown, and that by a certain set of manipulations you will derive a certain result. We cannot do everything in detail, but nevertheless we would like to understand at least how it works, right? How this tensor manipulation works and what kind of results can you obtain, which are quite clear and useful in the end. We have to understand that Einstein himself struggled with this mathematics for a long time. That is, around 1907, right after he developed special relativity, he understood that you could have a generalization of special relativity to accelerated frames, and he had some basic ideas on how to go about implement the physics and the concepts of it. But he did not know anything about differential geometry. It was a new topic. So eventually he got together with Marcel Grossmann, who was a buddy of his in Zurich, and the two of them Grossmann was in fact quite knowledgeable about differential geometry because his background was more in mathematics. And so Einstein and Grossmann, and then Einstein himself, for several years between 1907 or 1909 until 1916, struggled in understanding differential geometry, understanding the mathematical tools that would help him build up this theory. And it was quite a tour de force. So you will find, as I said, an outline of what we will discuss. I think up to about here, we are going to talk about general principles, how you construct the theory, how Einstein went about constructing the theory. We need to do a little bit of special relativity because it is only by doing special relativity the way we want to do it, the way Weinberg does it, we will understand then how to generalize it to general relativistic framework. So we have to do that. You will say, well, I already did special relativity as an undergraduate. Yes, you did, but not with this particular notation and with this particular emphasis. Looking, for example, at a perfect fluid, you know, how you formulate that, and because that later on generalizes to the general relativistic context. So anyhow, what about the book? Well, I have a list of books that I have. Again, it's on the course webpage, and let me briefly mention that. Sorry, that's the wrong document. Again, there is a rather long list, and I will not go through all of them. The book that we will most closely follow in this class, because of its very clear presentation, is Weinberg's book, which dates back to 1972. We're not going to cover the whole thing. Half of it is cosmology, which is somewhat outdated. Very well written at the time, but of course, you know, more than 40 years have gone by, so it's no longer up to date. I think cosmology, and in particular the observational aspects of it, have evolved tremendously since then. Things have changed because there's been so many satellite experiments. So, but nevertheless, the exposition of the general theory is done very well and very clearly here. So that's my book of choice. And you will find also some other books which I mentioned here. For example, Jim Hartel's book, which is fairly recent, is more at the undergraduate level, but because it was written so recently, it does have a lot of discussion of more recent experiments and things related to observational general relativity, tests of GR, and things like that. So as far as the more advanced books are concerned, I think the main ones, perhaps, that I would recommend that at some point maybe you have a look at, or go to the library, or whatever it is, maybe you can borrow it from one of your friends, are, so Weinberg's book, the one we'll be following mostly, Misner-Thorne-Wheeler, which is also called the phone book, because it's a thick black book with an apple in the front, and also referred to as MTW. Another classic came out about the same time as Weinberg's book, but the exposition is quite different. I think in the case of Misner-Thorne-Wheeler, it is general relativity is presented from a geometric point of view, emphasizing notions of geometry, curvature, you know, various things that are kind of more easily visualized. Weinberg's point of view is less geometric. He does not talk that much about the geometric aspect. He still views general relativity as a manifestation of a force carried by a particle, right? Particle physicist point of view. In fact, in Weinberg's book, you will notice that there's very few pictures and diagrams, whereas there's a lot of them in Misner-Thorne-Wheeler. Another book that I will lean on a little bit, and especially in the last part of the class, is Feynman's lectures on general relativity. Now, those used to be available at the Caltech bookstore for $7, and it was just a mimeograph set of notes taken by two of his students, Morinigo and Wagner. And now it's a book instead, and so it costs quite a bit more. What is interesting about Feynman's lectures is that it presents general relativity in a completely different way, as we shall see. He tries to derive it from quantum mechanics, which is very interesting and very original, as was often the case in his lectures. So other books that I will not talk too much about are Hawking and Ellis, The Large-Scale Structure of Space-Time, has somewhat of an emphasis on mathematical aspects of general relativity. Bernard Schutz's book is very recent, so it has some interesting new material. You can find Toft's lectures on general relativity on the internet, so they're kind of free. It's just a PDF file, and same for Carroll's lectures. And so as far as current research, cosmology, and also some classics by Pauli and Landau-Lifshitz are still available. In particular, Pauli's book is very interesting because it reflects already the kind of issues that people were struggling at the very beginning when general relativity was written down. And Pauli is, again, very original in his thoughts, and he already was mystified, for example, by the origin of the cosmological constant term and a number of other issues, which are very, very interesting to read about. So as far as cosmology per se, there's some excellent cosmology books out there. And as I said, we will just be concerned with the GR part of it and the very basic aspects. But if you want to read more about it, the books by Peeble and Weinberg are very nice and very thorough in their treatment. There's a lot of current research which we find in the form of various conference proceedings and things like that. At the very end, I will talk a little bit about the quantum theory of gravity. We'll only spend maybe 1 or 2 lectures on that because it's a complicated subject, and so there's books on that as well. I think they're not as thorough and comprehensive as in the case of the classical theory, because the classical theory was written down in 1916 in its almost complete form, whereas in the case of quantum gravity, people still struggle with trying to understand what exactly this theory of quantum gravity is. Right, so there's different viewpoints, and well, I think I like my own viewpoint too, and so I will take some stuff out of my own contribution. So anyhow, this is the general outline. So as I mentioned, I think to some of you, we will not have homeworks. You can assign your own homework. You can assign your own problems in raising and lowering indices or doing certain calculations having to do with tensor manipulations in GR. Weinberg does not have problems. Occasionally, I will mention certain things as exercises in class. There's lots of GR books that do have a lot of problems. And so if you're interested in practicing raising and lowering indices, you can do that by looking at these resources on the internet. And I encourage you to try to repeat certain calculations that we did do in class and filling in details and things of that sort. So as I said, the final will consist in a project, right? And so the idea is that you will pick a topic of your choice. Again, this you can find on the website for this class, and you can pick a topic of your choice. And I suggest a few here, but there's many others that maybe you can come up with and that will interest you. And you will do a 20-minute PowerPoint kind of presentation on that. So in the past, I had some very nice presentations done by the students, usually on things that we don't really have the time to cover in class. So for example, when it comes to, interesting problems in general relativity, for example, a rotating black hole is described by Kerr metric. Usually we don't discuss the Kerr metric in detail in this course because of lack of time. That would be a very good subject, for a presentation. We talk about 20 minutes about what happens if the black hole, instead of being static, is rotating. If you have a Schwarzschild solution that is rotating, then it's called the Kerr solution. And so things like that. And so I have a couple of pages on all sorts of things that could be of interest. And there's different emphasis, right? Some of these problems or topics are related to cosmology. Some are more mathematical. For example, you might be interested in learning how you do actually tensor algebra by computer, for example. There are some very sophisticated programs that do that, and so you could pick something like that. And so there's a little bit for everything, cosmology, and the quantum theory of gravity. So again, I encourage you to go and look at these topics and at some point make a decision on what you want to do a presentation on. And so let's see what else. I think at this point we are ready to kind of get started on the course itself. And so the first topic we're going to discuss is special relativity and how you already learn how to manipulate tensors and extract basic physical information out of the Lorentz transformation, how you construct invariants and things of that sort. But I thought, at least for the first lecture, it might be of interest to take a step back and look at gravity before 1916. So what was the state of gravity before Einstein's discovery of the relativistic theory of gravity, the relativistic field equations? So we are going to take a step back, and I think many of the things that I will discuss, you probably already knew about it and you have seen it at some point or another. For example, I will mention Kepler, right? Everybody is familiar with Kepler's law because you learned those laws when you were studying classical mechanics, right? But there are some other aspects that maybe you don't remember or you haven't seen, so I think it's interesting to bring it up. And well, I started out with just a single page on this thing, and then as time went on, it started to become longer and longer. And so I have here a few slides. Well, it's more than a few, but I will go very quickly through some of them. For example, in the case of Kepler, most of you remember what it was all about, so there's really not much of a point in discussing that aspect at length. But there's other things that maybe you didn't know or you haven't seen. So now, obviously, the whole idea of gravity and gravitation starts with the sun and the planets and the solar system and so forth. So it goes back to the Babylonians and the Greeks, who were the first ones to set up a system in which you could describe the universe. And at that time, gravity was pulling everything towards us, towards the ground. It was natural because we were at the center of the universe, right? So early formulations of astronomy and astronomical ideas put us at the center of the universe. So it was natural for objects to fall towards the center of the universe, and that was the initial explanation. There's a few pictures of that. The astronomical system that became well established at the time of the Greeks was one that was based on epicycles, that is, you had the Earth at the center of the universe and everything rotated about it, right? Now, the Greeks were early on realized that the planets were moving, right? Planetes means wanderers, so they noticed that there were some stars that were not fixed, but were wandering around. And so they figured out a system, in particular Ptolemy, by which these complicated motions could be described by circles within circles. And they constructed a theory that would explain all these different motions in terms of these epicycles. And this theory was developed about the 3rd century BC and lasted for about 1700 years. So until about the 15th century, people believed that in fact this was more or less the correct way to describe the universe, with us at the center, everything revolving around us, the planets moving around in epicycles to these very complicated orbits that were described by diagrams, but of course had no real underlying explanation, except that the Greeks, of course, favored circles, and everything that was done in terms of circles, and this epicycle theory was kind of based on that. So here's Ptolemy, and the system was very complicated, and in fact comments that were made later, like in this case in the 12th century, is that if the Lord Almighty had consulted me before embarking on creation, I would certainly have recommended something a lot simpler than that, because the theory was so complicated and somewhat arbitrary that it did not convince many people outside the scientific community. But nevertheless, it was the established truth for most people for about 17 centuries or so. And nevertheless, not all Greeks believed that this was indeed the correct way to view the universe, because a number of thinkers in Greece around the 4th to 2nd century started to believe that maybe things were a little bit more complicated. And remarkably, one of the first people that looked at the Earth and the Sun and so forth seemed to realize immediately that it was much more simpler to have the Earth to be some sort of spherical body. And Heraclitus of Pontus realized that this body would rotate about an axis. That was a simpler explanation, or perhaps the simplest explanation. It was natural for the Greeks to think in terms of spheres, so he thought, well, the Earth, why should it have some random shape? Let's make it spherical because that's an elegant form. And he noticed that it would rotate. And he concluded that it would rotate about its axis about every 24 hours. Now, this guy, Hipparchus of Nicaea, actually realized that not only does it rotate, but it also precesses. That is, he was able to establish that the axis of rotation moves around a little bit and in fact comes back to the same spot about every 26,000 years. So these were again rather sophisticated measurements, and Hipparchus was also able to calculate the distance through the moon, the distance to the moon, and estimate the size of the moon correctly already around the 2nd century BC. And so another important step in the development of this astronomical view of the universe that the Greek developed was Eratosthenes of Alexandria, who was, well, he was the head of the library here in Alexandria, which is on the Mediterranean in Egypt, facing the ocean. And he noticed that whenever a ship would come in from Greece, the first part he would see was the mast. So he said, well, you know, it looks like the Earth is not flat. It looks like it's rounded, which agreed with Hipparchus' ideas. And let me see if I can measure actually how round it is and what the curvature is. And so he had a grad student that he told him, you know, take a camel, and it's a 10-day camel ride. Go down here to Siena, which is around where today is Aswan. And at the summer solstice, which is the 21st of June, see what kind of shade you get in a well down there. And we can compare the shade in Aswan to the shade that I get from an obelisk or a well in Alexandria. And he noticed that the shade is different, which implies that there is an angle, which has to do with the fact that the two locations are at different latitudes. And by having his student or assistant measure that angle correctly, he was able to figure out that the Earth's circumference is what it is, to about 1%. Well, he actually measured it was 252,000 stadia, and of course to this day people debate on what exactly a stadium is, you know, how many meters is it. So his measurement was accurate to 1% or 16% or somewhere in between, depending on who you believe. And so he concluded the Earth was round. In fact, his measurement was much better than anything that Columbus had when he sailed off. Columbus' estimate for the diameter of the Earth was completely off. He should have used the Eratosthenes number, which was much better. And that's why he thought he landed in India, right, when he sailed across the Atlantic Ocean. Now, another very clever Greek was this Aristarchus of Samos, who not only was able to measure the distance between, again, like Hipparchus has done, between us and the moon and the size of the moon, but based on various occultations and angle measurements, he was able to estimate the distance of the sun. And he was actually, because of various uncertainties, he ended up being about a factor of 20 off, but he's the first one that actually developed a heliocentric system. So he put the sun at the center of the universe. He measured the distance between Earth and moon, size of the moon, measured the angles, and from that he was able to obtain the distance to the sun, and which is a remarkable achievement. That is why, if you look at this book, right, Aristarchus of Samos is now recognized as the ancient Copernicus. So it was not Copernicus that discovered the heliocentric system, it was actually Aristarchus. So then the question comes up, what happened in the intervening 1700 years, right? For almost 2,000 years, people believed in this nonsense of epicycles, even though the Greeks, apparently some of them, had figured out exactly what the solar system looked like, right? Which is quite remarkable. Well, what was the answer to that question? The answer was that it didn't suit the church that man was not at the center of the universe, right? Because the heliocentric system puts the sun at the center of our solar system and not man, not Earth, right? And so because of this fact, I think for a long time, these great discoveries that some of these extremely clever Greeks had done were just kind of forgotten and buried, right? Now, as far as gravity is concerned, Archimedes did not give important contributions. I mean, he studied levers and he did all sorts of ingenious mathematical calculations, but they don't have a direct bearing on what we will be talking about here. Nevertheless, he was the one that figured out how to calculate the center of gravity of a body. Archimedes, in fact, is recognized as perhaps the brightest mathematician of antiquity. And part of that is due to the fact that most of his work, by the way, is lost. We have it only described by other people. And the reason why he's regarded as such a bright mathematical genius is because he came very close to discovering integral calculus. That is, he estimated pi by doing Riemann sums, essentially. And that was already the 2nd century BC. Now, you think the Greeks were not good at computing, but in fact they discovered some remarkable, they constructed, I should say, some remarkable analog computers. This is, well, it looks at first like a piece of junk that was found in a shipwreck in 1907. It turns out to be a mathematical device to calculate the period of eclipses. So it's an astronomical analog computer. And at first you don't see much, but if you look at it closely, you will see that there are gears here. And this object lay around in a museum in Athens for a long time until people figured out that they could do X-ray tomography and look at the inside without destroying it. And so here's an X-ray image. And here is a reconstruction that is a picture from Scientific American that they did lately. And it is an amazingly sophisticated piece of machinery built in the 1st century BC to do astronomical calculations and calculate the motion of the planets and things like that. You can see how nice all these gears are. So again, the Greeks were very clever. A lot of what they did, not a lot, but a good part of what they did got lost. And whatever little we have left of these great writings of the Greeks, in fact, we owe that to the Arabs, because the Arabs were the ones that eventually transcribed it. And in Europe, most of that did not show up until the 15th century. Now, what about the Romans? What did the Romans do about gravity? Well, not very much. They couldn't care less. They couldn't care about astronomy and planets and none of that. They were interested in instruments of war and architecture and building great buildings and aqueducts and things like that. And so the only name I could come up with was basically Vitruvius, who was interested and did some study about density of materials. So he was basically a material scientist as far as physics is concerned. Well, his main job was as an architect, and he wrote some books on architecture. And in fact, the Pantheon in Rome, if you ever visit Rome, you'll be impressed by the Pantheon, which is 2,000 years old. That's the architecture of that was based on Vitruvius' writings, and how you would construct a cupola like this that would stay together and not, well, it lasted 2,000 years with all the earthquakes they have in Italy. That's pretty remarkable. Anyhow, that's the only contribution I could find or think of as far as the Romans were concerned. And well, in the Middle Ages, what happened to gravity and astronomy? Well, not a whole lot. Luckily, the Chinese at least were able to observe the Crab Nebula, which was a supernova that went off in 1054. There is no record of it in Western writing or Western literature, but we can see still what's left over today. And so we make this huge jump, right, from the 1st century BC to about 1500. And all of a sudden we have Copernicus that states that the sun is at the center of our universe and the planets revolve around it, including us. And so that's his discovery. Well, no, it was not his discovery, right? I mean, Aristarchus or Samos and all the other people in Greece had already figured that out with great precision, but nevertheless, this knowledge had been completely lost and buried by the church. Right? And so he wrote a book on this heliocentric system. And well, you wonder, how did he get it published? How did he get this book published in the 15th century? He had a friend. His friend was Luther. Martin Luther. They were both German, and in Germany there was no issue at that time because of the Reformation and the split with the Catholic Church to publish something that was as heretic as what Copernicus would talk about, namely that we were not at the center of the universe. And so the book got published. Now, again, Copernicus did not really add much to what the Greeks had already discovered. He just presented it again in a clear and homogeneous form. But soon after that, of course, there was a new interest in a heliocentric system, and that, in order to make some progress over what the Greeks had done, what was needed is better data. And so the first person that took that path was Tycho Brahe. And Mr. Brahe's contribution to gravity and astronomy is to do very accurate measurements of the motions of the planets, in particular Mars, Mercury, Venus, us, of course, being at the center of this solar system, and then Mars and Jupiter beyond it, and maybe Saturn. And interestingly enough, he did not have and did not use a telescope. So this was all done going out at night with some devices to measure the position over a number of months and years very accurately to see if there was some sort of regularity that was beyond what the Greeks had seen. So here are some of the contraptions that he used. Again, he did not have a telescope, so that is what he was using to measure his and his assistants to measure position. But his data was very good, was very accurate. He was very diligent in recording his data over long periods of time. And so his observations provided the basis for Kepler's work. Kepler is the one that looked at this bunch of data and all these dusty notebooks and said, well, there is a pattern, and the pattern is that the planets move on elliptical orbits. Right? So he thought first that maybe the motion was somewhat more complicated, but he immediately realized eventually that the ellipses were fitting the data perfectly, and that there was this great regularity that you already have seen in your classical mechanics class, where the orbits of planets are described by ellipses with the sun at one of the focuses. And so he thought that there was some force that was involved, right? And that force weakens when you go away from the sun. So there was a pull, and he thought that that would explain the elliptical orbits through some sort of pull that decreased with distance. But he did not have, a mathematical form for it. And nevertheless, this is the second law that he wrote down, which establishes a relationship between the swept areas and the interval of time. The wonderful thing about Google and the internet is that you don't have to write something like this or program something like this. You can just cut and paste and put it in your notebook. Kepler's law works very well because, of course, at his time, Uranus, Neptune, and Pluto had not been seen yet, but all the other ones had. And so if you take the square of the times of revolution divided by the semi-major axis cubed, you find that the ratio is very close to a constant, and the same constant for all these orbits. Right. Now, he also developed a telescope, and so that turned out to be useful. He observed a supernova, and so now the next character in line is not immediately Newton, but Galileo before him, because what Galileo did, one of his many achievements, because he did contribute in a number of different problems, one of his achievements was develop the telescope and look out at the skies and see what nobody had seen before. And so he developed what is called a Galilean telescope, which has a concave and a convex lens. And now if you go to a museum in Florence, you can see a reconstruction of all these telescopes that Galileo had devised. He did not invent a telescope because there were some Dutch glassmakers that had done something similar. They made some very nice lenses, but he's the first one that used it for astronomy. And so he pointed it towards the sky. Here's some of these telescopes. These are, of course, reproductions. Also some very accurate clocks, because to do astronomy you needed some good clocks as well. And so here is a page from his book where he describes Jupiter and the moons around it on different times, and you can see that his moons are dancing around, and he's trying to find a pattern. And well, he did his observations on the moons of the four main moons of Jupiter, because there's also some smaller ones, match very well with what is described in his book. And so why was this discovery remarkable? Well, first of all, nobody had seen it before, because you need a telescope to see Jupiter's moons. And secondly, because all of a sudden you have an example of a miniature solar system. You have a miniature solar system because you have something that is very similar to what we have in the solar system as a whole, where smaller bodies revolve around a big one. So he was very excited, and it was kind of an indirect, again, confirmation that the whole heliocentric system was correct, that there was some universal law of gravity. So he wrote to Kepler, and Kepler of course was very much impressed by these results, because it confirmed his ideas about the solar system. Another contribution which is relevant for this class from Galileo is that he noticed that the laws of physics, that is how bodies behave when they fall or when they roll down an incline and things like that, do not seem to be affected by whether you are sitting still in your lab or whether you're moving with a constant velocity. So the situation that he describes in his book is what would happen if you were doing some sort of physics experiments in a ship, right? Well, the ship rocks about a little bit, but let's assume that it doesn't, right? So it moves with uniform velocity, and that the sea is really calm, and then you would not be able to tell any difference. That is, things would behave the same way. In fact, you could play tennis or do some other experiment in there. And, well, you could look out through maybe, a window in the ship, but if you didn't have windows, you wouldn't really be able to tell that the ship was moving. It would be exactly the same if it was standing still. And this is called the principle of relativity, or in his case, the principle of Galilean relativity. Galilean relativity states that the laws of physics are unchanged if you're moving with constant velocity. So that there is no absolute motion or absolute rest, because you can't tell one from the other by doing any sort of experiment. The other important discovery that Galileo did, that you also learned about in your physics freshman classes at some point, is that in the absence of any sort of friction or drag, all bodies fall with the same acceleration, and therefore that you have g, the acceleration due to gravity, is equal to constant. And that is, in modern terms, is called the principle of equivalence. The principle of equivalence between inertial and gravitational mass. So all bodies fall exactly with the same g. And so again, as far as relevance to this class and relevance to a course about gravity and general relativity, we should mention Mr. Romer, because Romer was the first one to measure the speed of light and find that it was finite, right? And so he was aware of Galileo's discoveries of the motion of the major moons. And he said, well, these moons are supposed to have a certain period, right? 1 or 2 days or whatever it is. And so he tried to measure these periods by which the moons go around very accurately. And he found that things don't match, because these periods aren't constant. So either there's something fundamentally wrong with the laws of gravity, or there's something else that is going on. And the something else has to do with the fact that the Earth, throughout a year, is moving away or towards Jupiter. And therefore, it takes light a little bit longer to reach this point than it takes to reach this point. And that, of course, affects the periods of the orbit, and in particular, it affects the times at which these moons disappear behind Jupiter and then reappear on the other side, right? These times seem to fluctuate, and he was able to determine that the difference in time between here and there for the light signal to arrive is something of the order of 8 minutes. And so from that, he said, well, that could be explained by saying that light does not propagate instantaneously, that there is a time lag, and that it takes so many minutes for the light to get to a certain point. So he estimated that the speed of light is about 130,000 miles per second. There were apparently a number of errors that were done in this calculation at some point or another, maybe even transcription errors. So the number was somewhat off, but nevertheless, it is, it is in the right ballpark. So that was an important contribution. And after that, of course, it was improved by a number of different experiments, some of them just Earth-based, which were reduced the uncertainties in those numbers. Now, Newton's contributions, of course, we're all quite familiar, and so we usually discuss the fact that he was able, right, his most important contribution in the context of gravity is to explain Kepler's elliptical orbits and Kepler's law about equal areas in equal times and so forth in terms of a simple force law, right? Simple force law that says that this force that is exerted on the planets by the sun is proportional to their mass, inversely proportional to the distance squared, and has a new constant in front, which of course is Newton's constant. And then he went about to explaining all sorts of phenomena which before had not been understood, like the precession of the equinoxes and tides and things like that. And he was also able to finally calculate this effect of the precessions of the Earth rotation axis that Hipparchus had observed in terms, again, of oblateness of the Earth and pull by the moon and things like that. So now, of course, again, his key idea is that two bodies are attracted to each other by a force that is proportional to their individual masses. And that, of course, leads to a relationship between the gravitational constant G, Newton's constant, the big G, and gravity that is observed on the surface of the Earth. And so Newton was first able to give a number for that capital G. And already at the time, by him and by people that followed him, there were a few issues, right? There were a few issues that had to do with the fact that, first of all, it wasn't clear what exactly was responsible for this gravitational force, what is being exchanged. When you have forces on Earth, right, you attach a string to something and you pull that string. Here, the string is invisible, right? So there's something that is pulling on those planets, and well, it's just there, and it's a force, and that's the end of it. So the mediator of gravity was not understood and known for a long time. And the other thing that Newton and others understood is that in this model, right, the force of gravity is transmitted instantaneously, which might be slightly troublesome because Olaf Römer, of course, had shown that the speed of light is finite, right? That things do take a certain amount of time, and so Newton in his time was worried on whether gravity was exactly 1 over r squared or whether there might have been some corrections. And so over the centuries, people thought that maybe you could add extra terms like an inverse cube term. Laplace considered an exponential term, and some other people added various terms, and they tried to fit that to the data. And these corrections, of course, are very, very small. It turns out that general relativity does give such a correction, but it is a tiny effect. And so anyhow, at that time, nothing was seen, and Newton's law was established with great accuracy. Now, it is part of Newton's framework that he discusses everything in terms of absolute space and absolute time. That is, there is a notion of a preferred frame, which is the frame in which all these astronomical objects move, and there is a time which is the same for everybody, right? Some sort of universal time. And time, absolute time, exists independently of any perceived and it progresses at a constant pace throughout the universe, and it is some pervasive entity. And so in particular, he conceived the following experiment where you take a bucket, right, and you fill it with water, and normally, of course, the water is level inside the bucket, right? And now if you twist the bucket around, then the water will start to rise on the sides. And so why does it rise, right? What is different between the bucket at rest and the bucket that is rotating? Well, the bucket that is rotating is rotating with respect to something, right? Well, it's rotating with respect to the Earth. No, that's not a very good description because we know that the Earth is moving around in a complicated way. So Newton's explanation is that the bucket is rotating with respect to absolute space, right? So there's a notion of a preferred frame, which is like this. And when you rotate the bucket around, then you're moving it with respect to absolute space. And that explains why the water rises on the walls, right? And so that was the end of it. So absolute space would explain this effect, which is the same, of course, when you pirouette, right? At night, when you pirouette, your arms will go up, right? It's because you're rotating with respect to absolute space. And so we'll come back to that in a little bit, right? Because, of course, that's very relevant for general relativity, as we shall see. I mentioned here something else that is not directly related to gravity, certainly not to classical gravity, which is another important contribution of Newton. Newton thought that light was made out of particles, right? And, well, that turns out to be half right, right? Because we know that light is, in fact, both particles and waves. But this theory was, in fact, the dominant theory for a long time because Newton was such an influential physicist, in spite of the fact that Huygens thought that, if you were looking closely at various observations with light, you could see interference patterns and things like that, which pointed out to a wave-like nature. So, now, after Newton, a lot of developments had to do with the refinement of the theory in many different ways, including, of course, a more accurate determination of this Newton's constant that appeared in Newton's force expression. And Cavendish was one of the people that is first credited with measuring G accurately. Of course, Newton's original determination of G was based on the fact that you knew the acceleration on the surface of the Earth, the small g, and you can estimate for that the big G. But Cavendish actually took some large balls of heavy material, lead, and made them attract to each other and oscillate. And from the oscillation periods and various things, he was able to estimate G to an accuracy of about 1%. So this is a famous Cavendish experiment. And so you have two big balls and two small ones, and the small ones are connected by a wooden rod, and the wooden rod is hanging from on a steel wire, and you have what is essentially a torsion balance. And you can measure this motion very accurately because you can put a little mirror here, and you shine a light on the mirror, and then it comes back, and you can measure these things to great accuracy. So Cavendish's experiment, which was a laboratory experiment, had nothing to do with the solar system or the sun, right? It was a relatively small tabletop laboratory experiment, was able to measure this feeble attraction between these balls, right? They're about 30 centimeters, so it's about a foot, right, in diameter. Was able to measure that attraction quite accurately and establish the value of G from it. So if you go to Paris, you can find in the Pantheon a demonstration of the Earth's rotation through the form of a Foucault pendulum, right? So if you take a pendulum, well, you need to have a real big one so you can see the effect, because otherwise the normal pendulum slows down a little bit too quickly. So this one hangs from the top with a 67-meter long wire, so it's a real big one, and it goes on forever, swinging back and forth. And if you wait long enough, you can see that the pendulum rotates. Well, it's not the pendulum that is rotating, right? The pendulum always goes back and forth in the same direction, but the Earth is rotating, right? So the pendulum is maintaining its direction, but because of the Earth's rotation, if you look at what is happening in the Pantheon, it changes the direction of oscillation and eventually knocks down these little wood blocks, right? So if you wait, well, it takes a little bit. It's 11 degrees per hour, so you have to wait a few minutes, but after a while you can see that the pendulum is swinging about. Now, as far as gravity is concerned, again, not a whole lot happened as far as fundamental principles and ideas for quite a long time. Nevertheless, there were some important contributions. They were not entirely technical. We'll look at the technical ones in a moment. but which had to do with understanding some basic concepts. And in particular, Euler, right, who you know from his many contributions in mathematics, including Euler angles and the Euler formula for complex numbers and things like that. He was the first one to point out that, in fact, in gravity you have, apparently, based on Newton's theory, not one mass, but three. You have three different notions of mass, which apparently seem to be the same, right? It's the same number, but nevertheless, they seem to be conceptually different, right? And one is the inertial mass, that is a body's resistance to acceleration, right? The inertial mass has to do with inertia, which means that bodies don't like to change their state of motion. So if you push on them, there is a resistance to that change of state in their motion, and that's the inertial mass. There is another type of mass which at first seems to be unrelated to that, and that is the gravitational charge, if you want, in modern terms, right? The amount of gravity that a body exerts on another body, right? So the sun is a big body and exerts a lot of gravitational force on nearby celestial objects, and that's the active gravitational mass, which at first sight seems to have nothing to do with the resistance to acceleration, right? And the third gravitational mass is closely related to the active one, which is, of course, the fact that a body now is being pulled by the sun, right? And the amount of pull by the sun is proportional to the body's weight again. And so no wonder that our students are often confused about these three things, because if you look at them closely, they're actually three different notions, and they happen to be exactly the same one. And why that is the case, of course, is of great interest. I should add that nowadays one could do precision. Well, first of all, identifying these two is not a big deal. That the active and the passive one we can understand very quickly based on, for example, the electromagnetic analogy, for one, and the fact that they have, each one has their own gravitational charge, if you wish, which is the mass. But the puzzle that remains is, why is it the gravitational mass is the same as the inertial mass? And well, that is, of course, the principle of equivalence. And in principle, it is something that you can test. And to make a long story short, we know that these two masses are the same to 1 part in 10 to the 11. That is, one can do measurements of deviations of mi over mg being exactly equal to 1. And those experiments give that the principle of equivalence is good to about 1 part in 10 to the 11, right, nowadays. So it's certainly true, right, to a great accuracy, and the question is, why is it? Now, this principle of equivalence, namely the fact that the inertial and gravitational mass are the same, is the basis, as we shall see, of general relativity. General relativity can be based entirely on that, well, not entirely, but in great part on that principle. And so it is one of the cornerstones. It's therefore important to understand whether it is actually true or not, and if it is true, why is it true, and if it's not, then what are the deviations from it. So after Newton and Cavendish and so forth, there were no main new ideas for a long period of time, because people were really busy trying to figure out what exactly the predictions were of Newton's theory. And so that required some new mathematical tools that we usually learn when we take our classical mechanics class, which have to do with Lagrangians and Lagrange's equation and the principle of least action and so forth. And one of the first people that contributed to this was Laplace, who of course was able, well, one of the main contributions, if you wish, to gravity is his understanding that you could describe gravity, and of course it turns out to be true also for electromagnetism, in terms of a scalar potential, right? Even though you have a force, you can write that force as a gradient of a scalar, which is kind of neat, right? Because it reduces the number of fields you need to know from 3 to 1, right? And so he developed this Laplace's equation and Poisson's equation later on by Mr. Poisson. But these are kind of technical developments, aren't they, right? I mean, it's really no fundamental new ideas. Laplace also, at least, you know, for the kind of things that we'll be thinking about here, had an interesting idea, namely a body that would be massive enough that light would be bent back, right? And so he said, what happens if you have that the escape velocity for this body is equal to the speed of light, then what you would have is a radius that is in fact the same as the Schwarzschild radius. So he was the first one to consider something that we would describe today as some sort of black hole. And of course this calculation is complete rubbish, because you cannot take the kinetic energy of a body that moves at something like the speed of light to be 1/2 mv squared. So the coincidence of this number with the Schwarzschild radius in general relativity is completely accidental. Nevertheless, he did consider such very heavy bodies. And again, I mentioned Lagrange because of the Lagrangian and all the wonderful things he did, the development of celestial mechanics, finding out how you would calculate the motion of the planets using perturbation theory, and all these things that were very useful. And so we'll just skip all of that. And now there are some other developments which are, of course, of interest within the framework of this course, which have nothing to do with classical mechanics. They have to do with curved geometries, right? So some very clever mathematicians during the 19th centuries came up with the idea that you could consider spaces that were not Euclidean, were not flat, but had some curvature. And of course, the first ones to look at would be just two-dimensional manifolds like spheres and such. And Gauss is the first one that actually introduced the notion of curvature. That is, he said, if you have a manifold like one of these, right, you can locally define a notion of curvature. Not only that, but you can calculate that curvature in terms of a metric. That is, you can put a grid on these manifolds, right? You can define a metric. And once you have defined that metric by suitably calculating derivatives, which he wrote down, you can calculate the curvature at each point, which happens to be, in fact, an invariant that does not depend on the choice of coordinates. So he's the founder of differential geometry, if you wish, and therefore he's the founder of the whole line of mathematics that then led to Einstein's relativity. Nevertheless, Gauss only looked at surfaces, right? He only looked at surfaces. And so, for example, on Math World, you can find some of these wonderful formulas that Gauss wrote down having to do with the curvature of a manifold, written in terms of coefficients of the metric. This is kind of stuff we're going to discuss in a little bit, right? This is the line element, and G is the determinant of the metric. And he also wrote down which is called Gauss-Bonnet theorem. And so, nevertheless, he did just surfaces. And so later on, it was Riemann who said, well, you know, all these neat things that Gauss developed actually can be written down in higher dimensions as well, 3 and 4, except things get a little bit more complicated because you can have curvature in different directions. And so the math becomes significantly more hard. And right, so, well, we're going to talk about this differential geometry quite a bit, and that led eventually, of course, to Einstein understanding what were the mathematical tools that he needed to formulate this theory of gravity. But there is another very interesting individual who lived at the end of the 19th century, beginning of the 20th century, Ernest Mach, whom you probably heard about, but not everybody is too familiar with what he did, who questioned some of the basic principles of Newton's mechanics and Newton's laws, and in particular the notion of absolute space and absolute time were entirely revolting to Mr. Mach. Now, of course, Mach is mostly known for the Mach number, right? Everybody has heard about that, right? It has to do with airplanes and jets, right? And so he did important contributions as far as shock waves and things like that. But here we're interested in his contributions for gravity. So he wrote a book which is called The Science of Mechanics, in which, well, it's a set of lectures on classical mechanics, but he said this whole idea of absolute space and absolute time is just rubbish. You know, it's just theology. I mean, it is something that you know, you should do away when you talk about physical theories, right? So here's his book, German and English. And so he wrote down, enunciated what he thinks are the ideal of a physical theory, and that it should be based on directly observable phenomena, right? It's interesting that when we talk about quantum mechanics and Heisenberg, right, that's what Heisenberg emphasized, that, you know, when you formulate quantum mechanics, you should do away with all the things that you can't measure, you can't see, and you should just talk about observables. So Mach had the same point of view quite a few years before that. He said, we should not talk about things that we can't observe, that we really have no feeling for, and therefore absolute space and absolute time really have no place in the context of a physical theory. They should be replaced by something else. Okay, so what is that something else, right? So a bucket, when you rotate, the water goes up on the walls. Newton says, well, it's because it's rotating with respect to absolute space, or maybe it's rotating with respect to the Earth, but the Earth, of course, is moving. What happens in empty space away from the Earth? Well, it will still, when you rotate, the water will go up on the walls. So it has to be absolute space. Mach says, no, it's nonsense. The only thing that makes sense is that you're rotating with respect to the faraway stars. That's the only thing that makes sense, because that, of course, provides a reference frame, no matter where you are, if you are on Earth, but even if you are, you know, out in the middle of the solar system in some, you know, remote location, or even, you know, close to some star or somewhere in between. And so he says the notion of absolute space and time should be replaced as something that emerges from the large-scale distribution of matter in the universe. That is, inertia, this resistance of bodies to acceleration, whether it's linear or going around in a circle, that should be due to the distribution of mass in the universe, and that's the only way to understand it. And of course, that raises the question of what would happen to the laws of gravity if you were to remove all the faraway galaxies, right? What happens in that empty space? Do bodies still have an inertia, right? When you push a cart or you push an object, Mach says, well, it resists because you're moving it with respect to absolute space. No, that doesn't exist. You're moving it with respect to the faraway galaxies. But if the galaxies are away, if you remove all of them, then will it still have an inertia? And Mach says, no, probably not. So, right? So when you move an object, you're feeling the effects of the faraway galaxies, and that's called Mach's principle. Right? And then, of course, the question came up soon after that, right? And notice that you might think that it is speculative, but in fact, it seems something that is very natural to think about. And so soon after that, the question was, does Einstein's theory include Mach's principle? In other words, Einstein's theory is something that explains in a natural way the origin of inertia, the resistance of bodies to acceleration, things like that. And the answer is yes and no, because it includes some of Mach's ideas but does not explain this stuff here. So we'll come back to that, and of course that's very interesting questions within the concept of Einstein's theory to see to what extent, you know, it takes this into account. And Einstein, of course, later thought that his theory included some of Mach's ideas, and in particular it was referring to an effect that he and others calculated, which is called the Lense-Thirring effect. So we'll talk about the Lense-Thirring effect in class, and we'll come back to that. We don't have time today to talk about this. And so, but he wrote a letter to Mach, and he said, look, my theory actually has some of your ideas, Mr. Mach, Professor Mach. But Mach actually was never particularly enthusiastic about Einstein's theory. He didn't like it that much, which is kind of surprising. I mean, he was in his later years, and but it was kind of sad that Einstein, on the one hand, thought his theory incorporated Mach's principle, and on the other hand, Mach did not quite agree that this was the case. So it's called frame dragging. So this bucket thing and the existence or non-existence of absolute space, a preferred frame of reference provided by the faraway galaxies, is something that in part can be described by frame dragging. And it is of great interest even today because there are satellite experiments that actually want to show this frame dragging that is in part described by Einstein's theory through this lens-adhering effect. And so there was actually a satellite experiment in 2005 that was done to detect some of this frame dragging. And of course, I haven't said what frame dragging is, but we'll see that in this class, what it means. And so the other thing that of course had a profound influence on the development of, well, a number of physical theories, but certainly gravity as well, was the Michelson-Morley experiment that showed that there is no ether, right? Because in Maxwell's theory, you could think that there is a medium that permeates the universe, or at least our neighborhood, and that this ether is kind of static, and therefore if you move with respect to it, you'll see effects that are somewhat different than when you are at rest. So as you remember, because I think this is one of the standard things that we talk about in our classes, Michelson and Morley constructed this interferometer in which they had a beam of light that is split by this semi-reflecting mirror, and then it comes back both ways and is recombined, and through some sort of Fabry-Perot interferometer, they're able to see whether the interference pattern changes depending on whether the thing is moving or not, or whether, of course, the movement can be done just by the Earth itself, right? So depending on the orientation of this thing, you should be able to see effects according to what direction you pointed at and so forth. And none of that was seen, so there was no ether, right? So there's a vacuum, but there is no ether. And that was one of the bases of Einstein's special relativity, right? Because in Einstein's special relativity, all so-called inertial or observers that are moving with a uniform velocity with respect to each other, well, they're all the same, right? It's a complete democracy, right? There is no special frame when you move with respect to each other at a fixed velocity. And so that means that, of course, ether is out, because if there was an ether, then there would be a preferred frame, right? The frame in which the ether, you're at rest with the ether, right? So there is no such thing, and so that is what motivated Einstein to not to use that idea at all and build his special relativity on entirely different bases, right, and assumptions. So, as I said, this is, a brief history of gravity up to about 1907 or so, right? Because Einstein developed special relativity in 1905 and then immediately thought, what happens if these observers that I'm talking about, labeled by O and O prime, are not moving with respect to each other at constant velocity, right? If they're not moving back to each other at constant velocity, then the transformation between one frame and another is not the Lorentz law. Right? It's got to be something else. So one of the things that he immediately realized, and which provided a basis for constructing general relativity, is that there seem to exist special frames, and those are the freely falling ones. That is, if you are, for example, in a gravitational field, right, which does provide an acceleration little g, and you're at rest, right, there is a frame in which you fall down the Tower of Pisa or whatever it is, and in that frame there is no gravity, right? And so these freely falling frames are described by the laws of physics as they apply in the absence of acceleration, which means as they apply in the context of special relativity, right, where there is no acceleration, right? So if you're freely falling, then you have special relativity. If you're not freely falling, then it's more complicated. So he recognized that these freely falling frames play a certain role, and in fact we'll see that in this class, exactly what that role is and how that comes about, and how you formulate this in a way that is actually useful and can be extended mathematically. And so that was his starting point. And then he struggled for quite a while, because an idea is not the same as a theory, right? You have an idea, but now you have to formulate it in a way that is understandable, and preferably in terms of mathematical terms. And that was the struggle that he and Marcel Grossman had for a number of years, trying to understand what, how to put this thing together, right? So freely falling frames have no gravitational field, but now you need to describe this by a metric. And the metric will give you equations of motion, and when you do that, you recognize that you have things like the affine connection and the curvature that comes in, and eventually that led to the field equations, right? So in 1916, in the middle of the First World War, he was finally able to write down a set of equations that seemed to be consistent. And of course, those equations are just like Maxwell's equations, right? They're the Maxwell's equation for gravity. Right? If you put them side by side, you can recognize they're very similar structure. Right? There's also some very important differences. They're nonlinear because gravity attracts everything, and in fact gravity gravitates. So you have some fundamental differences with Maxwell's theory, but nevertheless there are profound analogies. And well, as soon as he wrote down the field equations, of course, he became aware there were all sorts of interesting effects, but also that there could be new terms that nobody had thought about before. By the way, I forgot to mention that the first idea that Einstein had was, of course, that gravity was a scalar field, like, where you have a Laplace's equation, you have a phi, and then you take the gradient, and that gives the force. Of course, that didn't work because it took him a little bit, but he realized that gravity is described by a much more complicated thing, which has 10 components, which is this metric, G mu nu. So there's 10 fields in gravity. There's 4 in electromagnetism, right? There's a vector potential and then the scalar potential. So 4 fields, which is a 4 vector in electromagnetism. In gravity, it's worse. There's 10 of them, okay? So the gravitational field is described by 10 fields, not 1, okay? All right, so anyhow, after he wrote down this field equations, he realized that he could have a cosmological constant. And so he became interested in what the effects were of that. And he realized that his solutions would give rise to an expanding universe. Everybody told him this was rubbish because the universe was not expanding. So he tried to find ways by which he could, take away this expansion of the universe. And then, around 1924, 1925, Edwin Hubble, right here in Mount Wilson, right, on a clear day you can see Mount Wilson. He had a big telescope, right, at his disposal, 100 inches mirror, right? So biggest telescope in the world at that time. So he points it to the faraway stars and galaxies, more importantly, and sees everything is moving away from us. So he says, "No, the universe is expanding, Mr. Einstein." Of course, everybody told Hubble that this was rubbish. No astrophysicist at first believed that this was correct. But eventually, I think it took a few years, and he was able to convince a number of people that, in fact, it was true, that his observations were not wrong, that, in fact, the universe was expanding. And that was, in the end, precisely what Einstein had predicted. Well, it's not fair to say that because, in fact, Einstein's theory predicts a number of different possibilities depending on initial conditions. You can have an expansion that then eventually recollapses, or you can have an expansion which expands indefinitely, right? Or you can have also, under certain conditions, a static universe. But certainly one which is expanding in the way that Hubble observed it is completely consistent and was, in fact, one of the natural solutions of the field equations. Right, so he first developed special relativity, and one of the cornerstones then of general relativity is this principle of equivalence. So it's based on that. So if this is wrong, then out goes part of GR. And so he realized very early on that even without having any sort of fundamental equations yet, in 1907, just based on this, just based on the fact that freely falling observers experienced no gravitational field, that clocks would slow down when you had gravity, right? So whenever you have a gravitational field on Earth, if you look at your watch, it will slow down. It does slow down as opposed to being just in empty space. But of course it slows down just by a little bit. And as I mentioned already, if you have gravitational fields, the natural way to describe them is to a curved space-time. And in 1911, he actually computes that light will be deflected by the sun, except he was off by a factor of 2 because he didn't have the full theory. He still was playing around with some sort of scalar theory of gravity as opposed to a tensor one. But he predicts that the light would be deflected by the sun. And well, it was lucky that nobody did an observation, because otherwise they would have proved him wrong immediately. So luckily, nobody had the time or the interest to do an observation yet. Then, of course, World War I broke out, so there was no way you could do these accurate measurements following an eclipse, you know, back in somewhere in Brazil or something. You board a steamer and there's a risk you'll be sunk on your way to Brazil during the war. So nothing happened until, this is what I mentioned already. So nothing happened until this original paper. By the way, you can find on the website the original paper. It's wonderful that nowadays with the web you can access, you know. It's in German. I'm sorry, you know, I don't have an English version. Maybe there's somewhere. But you can read the formulas. They're very similar to what we're going to do in class, in fact. And so, okay, I'll come to the deflection of light by sun in a second. But of course, there is a fundamental difference, as we shall see, between Einstein's theory and Newton's theory, because in Newton's theory, the motion of the planets is due to a force. In Einstein's theory, it's due because space-time is curved. Right? So it's a very different point of view. And, so here is Mr. Eglinton. So after the war was over, he boards the steamship, goes to Brazil, and he takes a picture of, well, you want to see that light gets deflected by the, starlight gets deflected by the sun. Most of the time, of course, you can't see a star near to the sun because the sun is too bright. But when there is an eclipse, then of course the sun is obscured and you can see the stars near to it, right, shining. And their position is going to be off. If Einstein is right, if there is deflection of light by the sun, then you think it's here, but it's actually there, right? So this is a picture of what Eddington observed. Well, the first observation was in 1919, but later it was done a little bit better in 1922, and so there's a picture of all the different stars' movements, right, due to the attraction of, well, what today would call photons, right, by the sun, and it all fitted perfectly, more or less. Now, of course, we come to today, right, 2014, and there's effects that all of us actually are using every day, which have to do with special relativity, because even when we talk about a GPS system, I wrote down here some of the numbers, because, right, you have a GPS system in your car. Many of us have something like this, and you have maybe a GPS, you know, in your iPad or phone, and because the satellite on which the GPS system is moving is moving at a certain speed, you can estimate that special relativity will give an effect which is of the order of 10 to the minus 10 correction due to the satellite movement. But general relativity also contributes, because the further you go up in a gravitational field, then gravity gets weaker. So the slowing down of clocks in a gravitational field goes away and the clocks run faster. And the gravitational effect is comparable to the special relativistic correction, and it comes in with this opposite sign. And now, the interesting aspect of it is that when you put in the numbers, time moves 38 microseconds a day faster when you are in one of these orbiting satellite. There's a constellation, I think, of 24 or 36 of these orbiting the Earth at about 20,000 kilometers altitude. And if you do not take the general relativistic correction into account, you will have a GPS drift which is 300 kilometers per month, So your position will be completely off. So the general relativistic correction is essential in getting these GPS systems to work. So, of course, other predictions of GR are black holes, right? And so here is a picture from the Getz group at UCLA who has been studying the orbits of stars around this pretty massive black hole that is at the center of our own galaxy, the Milky Way, right? For a number of years. They've mapped these orbits very accurately, and they've come to the conclusion that there is an object where the star is, right here, and which is rather massive. Its mass is estimated based on the configurations of the orbits at about 1 million solar masses or so. General relativity, as we shall see, predicts the existence of gravitational waves, that is, ripples in space-time, that if Einstein is correct, if things are going the way we expect based on Einstein's theory and also our understanding of quantum mechanics, I should say, right? It moves with a speed which is the same as the speed of light in a vacuum, and it has two polarization states, just like a photon, which is rather surprising because the metric, the gravitational field, has 10 components, but only 2 are physical. Just like for the photon, you have linearly polarized waves in the x and y direction if it propagates in the z. And so gravitation has the same thing. There's only 2 helicity states for a graviton. And of course, one of the topics of great interest in gravity research today is trying to detect this gravitational wave coming in, because if gravitational wave comes in, then it distorts the fabric of space and time, which means that if you have 2 big objects, they're going to get closer or further away when the gravitational wave comes in. So you have a huge laser interferometer, this is the one based in Louisiana, I believe, and there's 2 arms which are of order of a mile long or something like that, and they monitor for something coming in. Now, of course, in order to detect these things, you have to have a rather intense gravitational waves. So it's not enough, for some planetary motion to create such an event. You really need a nearby catastrophic event of some sort, like a coalescing binary, to emit a pulse of gravitational radiation that is going to be intense enough that it can be detected on Earth. Now remember, the intensity falls off as 1 over r squared, so it has to be really intense so that we can see something on Earth. Gravity, generally, its coupling is very weak, so we need a real big event to see something like that. Of course, gravity makes a number of predictions about cosmology. Of course, it doesn't predict everything, because there's some basic things that we don't know. One is the initial conditions, right? No matter what anybody will tell you, we don't know what the initial conditions were. We just run the movie back in time and see what the universe would look like very early on, but we do not know the initial conditions, right? We try to infer it from our observations. And also, there's a lot of ingredients in cosmology which have nothing to do with gravity. I mean, who knows what particles were around in the very early universe? We certainly know that there's going to be quarks and photons and electrons and neutrinos and gluons, you name it, but maybe some other things as well, right? So understanding the very early universe means that we understand what matter is made of, right, in its most intimate details, including the laws of quantum mechanics, the Pauli principle, and so forth. We understand a lot of it, but not all of it. There's a good part that we understand, but that has to do with gravity and other forces, but there's presumably other parts that we don't understand. Nevertheless, cosmology is a big deal nowadays because there's very accurate satellite experiments. So in cosmology, as far as gravitational issues are concerned, some of the basic questions, I mean, there's quite a few more, but some of the basic issues are, what is the geometry of the universe? Is there in fact a single universe or multiple universes or infinitely many? What is the source of curvature? In Einstein's theory, gravity is described by curvature. So what is the source? Well, it's matter. Yeah, sure, it's matter, but matter includes, of course, photons, radiation as well. But are there other things that we don't see directly? Some of it is dark matter, which is just some other form of matter that is not made out of baryons and stuff that we are made of. But there's also a cosmological constant. It seems that, in fact, this cosmological constant accounts for about 75% of stuff out there, some sort of vacuum energy. And of course, again, within the framework of this class, one of the questions that we would probably want to ask at the end of the course is, does the universe, or at least the parts that are supposed to be described by Einstein's equation, do these parts really obey the equations as we know them, or are there some other corrections which have to do with some additional terms, right? And so it's an observational issue, and also it's an issue of what other terms you could add to Einstein's equation. Now, we're basically done. This, I think, is the last slide or so. And so let me mention Feynman, because what Feynman tried to do, and this I'm going to discuss at the very end of this class, he said, well, Einstein's theory is beautiful. It's based on this very simple concept. It's based on the principle of general relativity, the equivalence between different observers, all wonderful. But we know, at least he thought, we know that the fundamental theory of nature is quantum mechanics. That really, right, nature is described by the laws of Heisenberg and Schrödinger and so forth. And that says that particles have mass and spin. There is this fundamental concept, right, that in quantum mechanics, this theorem that we do in the quantum mechanics class, we show that every particle has to have a spin which is 0, 1/2, 1, 3/2, or 2, and so forth, right? And no other values are allowed, right? You can't have spin 1/3. He says gravity must fall into that category, must be a particle. Of course, he had no doubt that there is a particle because it's a force, and that force is mediated by a particle, just like the photon. That particle has to have a certain spin, and spin 0 and spin 1 are ruled out because they don't give the right properties. For example, spin 1 will have oppositely charged particles, so it will have both attraction and repulsion, like you have in electromagnetism. That cannot be for gravity, because gravity is always attractive. So it cannot be spin 1, right? So it has to be something else, so he concludes it's spin 2. It's a spin 2 field, which gives rise, in fact, to a symmetric tensor. And then in this remarkable piece of work, which is part, in fact, of these Feynman lectures, because the Feynman lectures are about what I'm just talking about, he shows that if you write down the theory of a spin 2 particle that is massless, like the photon, has 0 mass, then you get Einstein's general relativity. You get just Einstein's general relativity, not more and not less. So that's remarkable. So Feynman derived Einstein's theory of general relativity by assuming that gravity is described by a spin 2 massless particle. It's almost a theorem, right? So it's important enough that it's something that we should talk about a little bit in this class, because I think he has a point. That quantum mechanics is the theory, right? Is the theory of the universe, not classical physics, right? So that leads, of course, to what is the quantum theory of gravity and how you combine classical gravity with fluctuations that have to do with quantum mechanics. So this course is about what is gravity? Is it force or is it a geometry? Why is it the way it is? Is it unique? Is Einstein's theory correct? And how does one test it? And what new effects does it predict that we haven't observed yet? And how would one extend Einstein's theory? In what directions would one extend it if it were to turn out that it's not the final answer? All right, thank you.